Part 2 of Lesson 2 in Chapter 1. We started talking about analyzing graphs of functions in the first part of Lesson 2. And now we're going to talk about symmetry. So we have three different types of symmetry that we're going to discuss on graphs. You can see the first one is symmetry with respect to the x-axis. And you can see on this graph, this has symmetry of the x-axis because if it contains the coordinate point like 2, 3, it would also have to contain the coordinate point 2, negative 3. The next type of symmetry that we talk about is symmetry of the y-axis. This graph has symmetry of the y-axis, and you can tell that because if it contains the coordinate point 2, 3, it would also contain the coordinate point negative 2, 3. Right there. Then our third type of symmetry is symmetry with respect to the origin. If there's symmetry of the origin, and it contains the coordinate point, let's say 2, 3, it would also contain the coordinate point negative 2, negative 3. Okay? So one way I'd like to help students remember this is go back to the x-axis for a second. When you look at symmetry of the x-axis, look at these two coordinate points. What value is the same, the x or the y value? The x value is the same. Now look at the example with the symmetry of the y-axis. Look at these two coordinate points. What value is the same? It's the y value that's the same. And if there's symmetry of the origin, you can see here what's the same, the x or the y value? Neither. They're both opposite of each other. So those are three types of symmetry. Now, with symmetry with respect to the y-axis, we give a name to that type of function. We call it an even function. Okay? And then if there's symmetry with respect to the origin, the name we give that is we call it an odd function. So keeping that in mind, you're going to be asked to test for symmetry. So here's an equation, and I've hidden the graph for the moment. It says use the graph of each equation to test for symmetry with respect to the x-axis, the y-axis, and the origin. Support the answer numerically. We are going to do that. And then it says confirm algebraically. We're not going to do that. So with this equation, if it has a y squared, it's going to be a u-shaped parabola curve. Normally, if it has an x squared, it's a u-shaped parabola curve that opens up or down. But since this one has a y squared, it's going to open either left or right. So normally you get y by itself. On this particular equation, you get x by itself, and that would give you a u-shaped parabola curve that opens to the right. So as you look at this graph, it should be pretty easy to tell that there's symmetry of the x-axis. And so if we look at some coordinate points, like this point right here, which is at 2, 1, then it should also contain the coordinate point 2, negative 1, which it does. 2, negative 1 is right here. This is the confirming the answer, supporting it, I should say, numerically. Now I want you to do two sets of points. So let's come up with another point on this curve, which is 5, 2, right there. And if it has 5, 2, it should also contain the coordinate point 5, negative 2. And it does, as 5, negative 2 is right there. Okay, so that's confirming it numerically. I suppose I should say it's symmetry of x-axis. Next one. Again, I've hidden the graph for the moment. This is x times y equals 4. We're going to figure out what type of symmetry that has. Well, this ends up being a rational function. Back in Algebra 2, you guys learned how to graph these. If we get y by itself, we get the equation y equals 4 over x. This produces a rational function. There is one undefined value. We've been talking a lot about domain. And the domain of this function would be all real numbers except for 0. Why isn't 0 in the domain? Because if you put 0 into this function, it gives you 4 over 0, and that's not a number. So that graph would look like this. It's a rational function. There's a vertical asymptote right here at x equals 0. There's a horizontal asymptote right here at y equals 0. And so if we're going to confirm this numerically, let's first determine what type of symmetry it has. It's symmetry of the origin. And so if we take a coordinate point such as 2, 2, then it should also have the coordinate point -2, -2. And you can see both those points exist on this graph. Let's come up with another coordinate point. This coordinate point would have 1, 4. And if it had 1, 4, it should also have -1, -4. And you can see both of those points exist. Right here is 1, 4. And -1, -4 would be located right there. So that's how we're going to, again, support the answer numerically. We're not going to confirm it algebraically. A couple more examples. 5a, you can see that this has symmetry of the y-axis. So, find some coordinate points such as 2, 2. If it has 2, 2, it should also have the coordinate point -2, +2. And you can see both of those coordinate points. Here's the 2, 2. Here's -2, +2. If we produce another coordinate point, such as, let's go with 1, 5, then it should also have the coordinate point -1, +5. So that confirms it numerically. Now 5b has all three types of symmetry. And so to confirm this is a little bit more, but let's take a coordinate point such as, let's see here, how about 3, 4. You can see the coordinate point 3, 4 is located right there. And so if there's symmetry of the x-axis, then it should also contain the coordinate point 3, -4, which it has right here. And if there's symmetry of the y-axis, it should also have the coordinate point -3, 4, which it does have right here. And then if there's symmetry of the origin, it should also contain the coordinate point -3, -4, which it does right here. So all four types of symmetry exist on that problem. And if we were to find another coordinate point, let's do it in green, choose the coordinate point 4, 3. 4, 3 is located right here. And so if it has that coordinate point and there's symmetry of the x-axis, it should also contain the coordinate point 4, -3, which it does right here. If there's symmetry of the y-axis, it should also contain the coordinate point -4, +3, which it does right here. And if there's symmetry of the origin, it should contain the coordinate point -4, -3, which it does right here. So there's supporting it numerically. Okay, last two examples here. Use the graph of the equation to test for symmetry. You can see on this one we have symmetry of the x-axis. And so if we find a coordinate point such as, let's see here, let's go with -2, 1 right there. If we have -2, 1, we should also have the coordinate point -2, -1. And it does have both of those points. Another coordinate point I'm going to select is going to be 1, 2. And if it has 1, 2, it should also have 1, -2. And it has both of those coordinate points right here. There's 1, 2. Here's 1, -2. So that confirms it numerically, or supports it numerically. The next one is just a line, and this is not obviously showing symmetry of the y-axis or the x-axis, but I believe it is showing symmetry of the origin. So, to confirm this, if we take a coordinate point such as -2, +2, it should also contain the coordinate point 2, -2. And if we look at those two coordinate points, here's the -2, 2. Here is the +2, -2. And a second pair of points, let's take -3, +3. It should also contain the coordinate point 3, -3. And here are those 2 points. So that supports it numerically.